How's it going, ladies and gentlemen? Mr. Johnny here again, taking a look at chapters 16.10 and 11 stuff. Here are the objectives. Pause it, read through them, come back to them at the end, see how you feel about them. Let's jump into it. All right, so it says one of the following, which is the strongest acid? So if I were to draw these out, all right, I got H, I, and then O off of that versus H, I with two O's off of that, and H, I with three O's. All right, and then HI with four O's off of that. Now the question is, which one's the strongest acid? Well, the strongest acid is going to be the one with the weakest bond between hydrogen and that iodine, right? So we're talking about these bonds right here. Which one's going to be the weakest? Well, they're both between hydrogen and iodine in all of these things, but the rest of the structure affects the strength of that bond. So if we take a look, we know oxygen is a really electronegative atom. It likes to hog electrons. So the more electrons are being pulled away from that hydrogen, the weaker that bond's going to be. The easier it is for that H to pop off. I kind of think of it like, this iodine would be like the mama pig, and then we got all these other baby pigs trying to, get into the mama pig so they can feed and whatnot. And then hydrogen's kind of the run, right? So the more oxygens we have around the iodine, the more it's pulling electrons away from that, the weaker the bond between the hydrogen and the iodine is going to be. So the strongest acid is going to be the one with the more electronegative atoms bonded to that central atom. It's going to have to be D, HiO4, right? Because kind of what's happening is these oxygens are hogging up all those electrons that iodine's got, and hydrogen's getting bullied out like it's the run of the litter. All right, so number two, of the following, which is the weakest acid? So it's the same thing but different, right? So if I just go back real quick, HiO4 was the strongest acid because it had the weakest hydrogen iodine bond. Well, which one's going to have the strongest bond? Which one's going to be the least likely to pop out a hydrogen? It's going to be choice A. All right, and then three, which of the following acids will be the strongest? All right, well, let's take a look. We got SO3s and we got SO4s. Well, which one's going to be stronger? The one with more oxygens is going to be more likely to kick off a hydrogen. So I can get rid of those two choices. So now it's down between which two? Well, three of these, right? A, B, and D. So we look at them. Well, HSO4 has a negative charge to it. So it's going to hold on to that positive hydrogen stronger than if it was neutral. So B's not looking too good either. All right, so now we got H2SO4 and we got H2SeO4. All right, well, if we take a look, S is more electronegative than Se, so it's going to be pulling more electrons away from that hydrogen too, which would make it the strongest one. And you might also be able to cheat and go, well, I just know that's a strong acid, and none of the rest of them are strong acids too. So if you can remember which ones are strong acids, this problem was a piece of cake as well. All right, so in the gas phase reaction below, NH3 is acting as a blank base, but not as a blank base. All right, so we got definitions here. Let's talk about it. We got the Arrhenius definition for base, gives an OH minus. We got the Bronsted-Lowry definition, which is a proton or an H plus acceptor. And we have the Lewis definition, where it is an electron pair donor. So those are the three definitions, right? So let's draw out what's happening. We got NH3. It's got a lone pair of electrons up here. And we got H plus, a proton flying around. And it reacts to give us NH4 plus. That whole thing has a positive charge. So what happened here? Well, NH3 was a proton acceptor, right? It accepted a proton, but it also donated electrons. So it could have been a Bronsted-Lowry base, or it could have been a Lewis base, but it definitely was not an Arrhenius base. right? That definitely was not. So we know that it has to have that as my second option. And there's only one of these things that fit E. It was acting as a Lewis base, but not as an Arrhenius base. Remember, if I were to draw like a circle or something, 3 circles, right? We got the Arrhenius is the most specific. We got Bronsted-Lowry is a little less specific. Then we got the Lewis, which is the most general definition for acids and bases. So Lewis is the most inclusive, Bronsted-Lowry the second most inclusive, and Arrhenius is the least inclusive definition for acids and bases. Hope that helped. See you in class.